Start, please record. It's on? Okay, thanks. Okay, actually we somewhat finish it without some sort of the classic 5 classical chapters. We are already introduced to you the very general system of hydrodynamic. Now we Stokes equation, divergence-free equation. Then we find the just trophic flow, and later we found that there is a boundary condition which we imposed here for slightly differential rotation. And all these states are sort of the classical problem. Eventually we went to the very difficult situation about shear layer. Before that we discussed the boundary layer. So it's sort of, it was the example of sort of the classical problem. And so now later, today and tomorrow, later you will have your own presentation and you show what you understand from this classical point of view. But now we somewhat finished this classical approach and go to the field which is very deeply linked to the with the real situation in the planetary core. And it's of course the most important subject. Of course, we cannot consider all the situation in the planetary core, but we just stop ourselves on convection, and not all convection, but the convection which is almost adiabatic. And in short, we have this model of the spherical shell, which is responsible in very deep interiors of the planet, or maybe moon, which is consists, in case of the Earth, it consists from the mantle, which is on which we are on the outer boundary of this mantle. We are living creature, doing the hopefully very well, and thinking how to approximate the liquid core here deep inside. And this liquid core is actually consists basically from the ferrum, and there is some small addition of the other element, and also it's actually worked by the thermal production of the corresponding Archimedean buoyancy flow, and it's actually creates the convection. And also some big role in case of our Earth play is the inner core, which is slightly more heavier in terms of density than the outer core, which is from fluid, just because the heavy component is descending on this inner core, while a lighter component is going up. So this is one of the mechanisms which work to drive the dynamo. There is more simple mechanism which we basically more often will discuss. But of course, all these mechanisms are similar, and this another mechanism is actually related just that this initially very hot liquid core is just cooling down, and during this cool, also some Archimedean acceleration arise, which drives this dynamo system. No, sorry, not dynamo system, this convection system. So actually, the first things which work here is the energy of this heat flow or compositional flow. And here I will say you how to obtain the initial equation for this situation. All of them, the equation from which we are actually started, are written here. It's has 4.1, but let's discuss them a little bit more detail and start from some introduction. So this chapter 4 actually, which has a name. Okay. This chapter 4 And this is basic equations. For planetary convection, actually. Actually, moon, maybe moon also can work. Convection. In this chapter, initially complex system of planetary convection equation is simplified. This is a very important point, that we simplify it to a system no more complex, which is almost adiabatic approximation. And so this is the results of the system make it possible to use the accumulated experience of studying thermal convection in a rapidly rotating viscous spherical layer. And let me just stress that the majority of all the studies were related to the heat transfer equation. But more general way is to apply the entropy equation. And in this case, we can actually proceed with much more, with much less errors, and to make the good approximation. And also nonlinear scales and velocity of planetary convection are estimated. It's also will be in this introductory lecture. And this estimation will be based on the parameters known from observation under condition of small dissipation compared to the kinetic and turbulent effects. And the major point here, as I told you, of all this approach is that viscosity in some sense is very small, because eventually we will see that it will go like an Ekman number. So this number is small, but it's near the higher order derivatives. And it's allow to dramatically simplify all the system. But let's start first of all from the initial equation. So we proceed to the first paragraph in this chapter. It just will be named in the same way, 4.1. So it will be just initial equations, and simplification. Of course, we writing down here that there is simplification, but it's not so severe actually, because we will later estimate how much is the simplification in our approach, and you see that it has very good accuracy. So we will write the law of conservation of mass first of all, using the full spatial derivatives. So actually we use the full spatial derivatives, which is by definition d over dt, capital D, is equal, perhaps you know it, I just repeat you, d by dt plus v grad v times grad. So, and just to distinguish the vector field, we put vector here because it's quite difficult in this notation to make them as a fat variable. So this is no, and of course it's a result using this stuff. We have rather standard form of the continuity equation, which relate on the density. And this is equal minus rho divergency V. Okay, this constitutes the very first formula, 4.1a. And of course, everybody knows that which equation we will write down the next What do you think? The next equation, of course, will be Navier-Stokes equation, no doubt. But more precisely speaking, if we consider the Navier-Stokes equation, it's include continuity equation as well. So usually people, maybe not usually, but very often people presume that if we write down this precisely Navier-Stokes equation, which is some analog of the second law of Newton, and so somebody supposed that this is the Navier-Stokes equation. But originally Navier and Stokes, especially Stokes, they stressed that it's the system of equation, complete system of the equation, which have the continuity equation and Navier-Stokes equation. So we write Newton's second law in the form of Navier-Stokes equation for acceleration in coordinate system rotating around a unit vector. A unit vector here we will use more common notation, because before that I will be using notation for the unit vector, which is from my point of view quite convenient, which is represented via the gradients of the coordinate, and then we can very easily manipulate with all these unit vectors. But more common way just directly to designate this unit vector, and usually people, if they consider this situation like here, there is angular rotational rate which is directed in this direction. So everything is rotated around this angular rotational rate, and so there is some selected direction in which we have this unit vector which is along the axis of rotation. And so maybe more general notation for this vector is like that. So one vector, and here we just put that. It's more general representation. Of course, if in my notation it will be grad z. So I think that it's more convenient, but more common use. And if we even take more specifically, here just because to distinguish vector value from the scalar value, I'm using this arrow on the top. But usually, of course, people use fat stuff. They wrote it like some that. 1 over z. But it's not so easy. So I prefer to use this arrow things. So we have a unit vector 1z with a constant angular velocity. So in total, we have that everything is rotated is 1z, and the full vector will be, okay, let's write it this way, should be multiplied on the module of the angular rotational rate. So it will be, and it's useful to have the value of this angular rotational rate. For the Earth case, it's approximately, but it's very good accuracy. It is 7 10 to minus fifth per second. It's by the way, it's quite valuable value, because if you multiply it by the typical velocity or typical scale, you will get rather strong rotation. So if you just multiply by the radius, you will have some hundreds of per second, 100 meters per second. So it's quite big, and maybe you know that you should even take it into consideration when you are traveling or using some gravitational stuff, and it's resulting this acceleration result in some very big addition to the gravitational force, which has a value about just a little bit less than 1%. its sufficient value. So as I already commented, let's now write down this Newton's second, more correctly to name it not Navier-Stokes equation, but analog of Newton's second law, or sometimes it's even more often it's named just momentum equation. Momentum equation. Maybe the most often the name of this equation. And of course, it's very, very familiar for everybody equation. I will just write down. Again, it's represented via the spatial derivatives or substantial derivatives. There is different name for these derivatives. So actually, it's maybe convenient, first of all, to write it in this form, because we have the spatial derivatives. In some sense, this is full analog of the acceleration, which was in the Newton law. So it's, but of course, divided on the density. So if we divide it on the density, then the first things which is most important is the things which are responsible for the viscosity process. And as already told, the most important ingredient of it is which is related to nu, kinematic coefficient of the velocity, and of the viscosity, sorry. And it's divided by rho, and it's more convenient and right is to use not Laplacian, but maybe double rotor. It's actually the same in some extent, but it seems more convenient just to make the corresponding expansion of all this term. And also there is another contribution to the viscosity. This is related in such a number, and again rho, and it's actually connected with the continuity, and it could be represented like that. You will take the gradient of divergence of the velocity. So in the Earth case, of course, this term is the most important. And that one is more become important in the stars or everywhere, but mainly in the application which we consider with you, it will be not so important. But let's keep it for the moment, because we start from the very beginning. And the next term, perhaps comparable, is in value, and in value in the boundaries, but maybe even more important in the bulk of the inner core in this direction. So you say that the viscous term is very much important on the boundary here, and also in the shell layer, as we show you in the previous lecture. But the Coriolis force is important everywhere, except the boundary layer. In the boundary layer, this boundary layer structure is common force, but in outside the boundary, in the bulk of the liquid core, this Coriolis force is very much important, except of course the tangent cylinder, this tiny amount, but everywhere this is very important. So actually we write down this Coriolis force, and this Coriolis force appears very naturally from the point of view that we are in the rotating system. And if you remember, we started our course from the rotating system and derived the equation. So in this rotational system, this Coriolis force appear very naturally. Of course, here we put the module, then we put unit vector in direction of z in the axis of rotation, and it's just cross to the velocity vector. Okay, what else remains? Of course, there is thermodynamical pressure. It's also play a rather important role because it's of order of Coriolis force. And the least, but in a very sense, it should become very, very first. It's just gravitational potential. There is gravitation influence U, and so there is a gravitational potential U, and it's perhaps the most important part of all this stuff, because it actually drives the convection. Because namely, due to the influence of gravitational force, we have, for example, if we consider the thermal situation, then some bubble is warming up and it go up. So when it go up with this warming bubble, so it's produced directly this energy to convection directly from this gravity potential, because just it's going up, and so this is actually due to the different gravity in the surrounding region, and there is some deviation of the gravity which we consider later. So eventually, of course, even in the case of the temperature, we have this gravitational effect, which is also called Archimedean force effect, and so on. It's just because the sinks, the heated sinks, becomes lighter and going up. And so this is a purely gravitational effect. And or another situation, if we consider the concentration, so the concentration the same role it plays, but maybe in opposite direction. If in the heating we see that it's going up, but here we have the light, heavy addition, heavy part of the wall convection, which is working in this fluid core. So there is some mixture of the more heavy component and lighter component, and this heavy component, again, due to the gravity, directly due to the gravity. In this case, if in thermal way we make somewhat indirect influence, but eventually gravitational. Here, in the case when we have that the part of the liquid core, which is more heavier, going down, it's direct gravitational effect. It's direct gravitational effect because just it's more heavier and it goes down. So, and it's also working, but in this case, it's not important to in which direction, up or down, but anyhow, convection appears. So let's enumerate this formula. I've enumerated here for 1b. Okay, I just show that it's this formula. So we consider dynamical viscosity coefficient eta and xi. We consider eta and xi dynamical coefficient, which was introduced in the maybe very famous course Landau and Lifshitz. It's very, I've seen the most classical course of the theoretical physics. And there is even joke about this course that in this course there is no any thoughts of the Lifshitz and no any words of the Landau. So all the ideas, everything, all the physical idea is by Landau, but all the wording, all the words, all the explanation are by Lifshitz. So they have some sort of the separation. So they say that there is no any words in this famous course of the Lifshitz, well, of Landau, sorry, but there is also not any theory from the Lifshitz. Of course, it's just a joke, but it's interesting separation of the other, because Landau is very, very famous Russian scientist, one of the Nobel Prize winner. So he invented very many things. But sometimes it was difficult for him to explain what he invented, what he suggested. So appearance such a person like Lifshitz was vitally necessary because he understands what Landau is formulated and then tune it to maybe more simple language and people understand, and now they enjoy with this. Perhaps maybe it's the best course of the theoretical physics, and I don't remember how many books are there, but maybe 10 or something like that, and a very big book books. So actually this dynamical coefficient of viscosity we use from Landau-Lifshitz, but also there is some relation to the our coefficient, that here we use some substitute, because here in their original notation he has for this value, which is written here like zeta, so we just actually replace it with more complicated stuff in the original representation, which is could be written like that. Divide by 3. So we replace it just for the sake of the simplicity, because to manage with such an extended coefficient is not so convenient. So we introduced, instead of it, we introduced that. And this is actually from Landau-Lifshitz. I don't know, Landau-Lifshitz. Actually, if you consider the direct, one of the recent edition of this course, it's 213. So, but maybe it's not so important, because actually later we'll get this one, but let's keep it for the moment. So, since even their order of magnitude is, it's not so important how we represent this viscosity coefficient, because this is the most poorly known value. We only can state that it's in some terms, in some relative term, it's very small. So in accordance with our accuracy, it's quite convenient everywhere. After that, we will just consider this viscosity coefficient as a constant. And as I already told you, in some practical application, we will neglect this coefficient. So we can even make like that by puncture that. In some sense, we can remove that. Okay. So the confidently determined angular velocity of rotation of planets and moons, omega, is large enough for the acceleration, often and not quite correctly called force, of Coriolis to dominate in 4.1. As already to dominate in 4.1b. As I already told you that there is a sort of the domination of the Coriolis force, but it's maybe not so correct name, because it's not a force. It's virtually more related not the force, but the acceleration. You see that just in dimensional consideration, it's better to name it acceleration. But usually physics they name it force, and it's still named force, while it's of course acceleration. So it's dominating for 1b and compensated mainly by acceleration associated with pressure. And the easiest term to compensate it is, of course, pressure. So this is compensation preferably working in this way. This compensated first of all with this. Okay. The dynamic equilibrium in 4.1b is controlled by the potential U from Newton's law of gravity, and so it's actually could be also writing down this Newton law of gravity in the differential form for this situation which we have. This very famous law, one of the first law, could be easily written down. There is a delta squared or nabla. In the scalar cases, they are indistinguishable. And this is equal in the C system for P, gravitational constant, and rho. This is very simple equation to which the gravitational potential obey. And you know that actually we start from this equation, then we exclude it somehow just to make finally the term that which is responsible for the convection. So this is formula 4.1c. And here there is a gravitational constant, which in C units is equal C.67 over the 10 to minus 11. And accordingly, it could be measured in inverse square of the second, then inverse cube of the meters, and finally it's divided by kilogram. So this is the constant, gravitational constant, and in, okay, so we numerated this. So in 4.1b and further, we will not take into account centrifugal acceleration. Of course, as already you can understand, when something is rotating, so there is some centrifugal acceleration, but we will not take into account. And this not taken into account constitute only fraction of a percent of the gravitational acceleration. Gravitational acceleration, actually, the gravitational acceleration on the boundary is about, on the outer boundary, GO, is actually equal module of gravitational potential, full gravitational potential at R equal RO. On this picture, this R equal RO corresponds to this boundary. And it's slightly more than what we observe on the surface. And this is about 11 meters per square second. So this value at the outer boundary of the liquid spherical shell, which I show you, in the deep interior of the planets of the moon, or moon, of course. The spherical radius of this outer boundary is about 3,500 kilometers. So this RO, we just can write down the value for the Earth. This RO is measured quite precisely by the seismical method, 3,500 kilometers in the Earth. And further, we, of course, as we did previously with you, we just denote this radius by the subscript O, just to indicate that this is the outer boundary layer. And what is regarding the centrifugal force with such a numbers, of course, it's not so important. It's even less than 1%. So we can safely neglect by this centrifugal force. And at the inner boundary of the liquid core, there is another radius which we, as we did, denote as in previous our notation, like Ri, and its value is 1022. Quite a good number. 222. Okay, in the Earth, of course, again. Okay. And to close the system for 1, we have the system for 1. Two more thermodynamic further equations are needed for the density and pressure P. You see that there is 3 variables, because velocity, very initial stuff which we are looking for, this velocity is constitutes 3 variables. Then there is the pressure, there is the density, and there is a gravitational potential. So in total we have 6 variables. And then you see that at the moment we just satisfy have 4 equations, because this Newton law of in the form of second Newton law, or momentum equation, maybe just name it momentum equation, it's more easier. This momentum equation, because there is 3 components, it constitutes 3 equations, and this continuity equation, this one, it's this one, it's 1 equation. So we have 4 equations. So we need another 2. We need, we have 5th equation about this. So we just need 1 more equation. And we, of course, get it from the thermodynamics estimation. To close the system for 1, 2 more thermodynamical, or we just shorten thermodynamical just for TD. Further, we just shorten that. So we need 2 more thermodynamic equations are needed to density and pressure P. As the first dynamic equation, we will choose the law of conservation of energy. And again, we reference to the same book of the Landau, Lifshitz, and it's in accordance with this, his paragraph 49 from his book. So we will write the law of conservation of energy in the form of general equation of heat transfer for the specific per kilogram of mass entropy S. So you see that now appear 1 more variable. So if we have here 5, so if we adding the entropy, so already we should have 7. So we have formulate 2 more equations, as it's said. So why we use an entropy? Because in entropy it's in the most simplest way. Everything could be expressed. So we will write the law of conservation of energy in the form of a general equation of heat transfer for specific. Specific, it means that per kilogram of mass, entropy S. S capital is our entropy, and the law of conservation of energy. So we just write down energy law. It's also, of course, rather classical. We take it directly from the Landau-Lifshitz course. Rho T. T is the thermodynamical temperature. Then we have substantial derivatives. From the entropy, S is the entropy. And it's equal. Okay, I should move here. No, we're still there here. This next step. So we have this equation of the entropy, which act on the sort of Laplacian, but a bit more complicated stuff. Capital K, gradient T. And there are various sources of heat, which all of them we just put in one small q. And this is equation 4.1 d. Here K is the thermal conductivity. You can write it down. K is the thermal conductivity. Thermal conductivity. And Q is the power of radioactive, dissipative, etc. local heat sources. So it includes everything what we can imagine. But in the case of the Earth, perhaps the most important is the dissipative, while radioactive also played in force, but maybe in more ancient time. As it is done in the Busse approximation, maybe it's interesting that Busse approximation, he formulated his approximation in 1903. But it was a person, Oberbeck, and who formulated about 16 years earlier. He, or maybe even she, by the way. I forget exactly, but maybe it was not he, but she. This he or she formulated it in 1997. No, not 97, 1897. So it was before 16 years before the Busse. And all the glory is with Busse, but not everybody remember Oberbeck. So the temperature T can be further chosen together with pressure P as the main thermodynamical variable. So the remaining thermodynamical variables are expressed through the main variable using the identical form of the another course of the Landau-Lifshitz, which was also in another year, 1995, which was connected more with thermodynamic. Okay. However, as shown in the section 4.4 below, so the first idea is just to make usual, simple representation via the using thermodynamical pressure and thermodynamical temperature as an initial variable. But there is a special task in section 4.4, which I will discuss you below. So such a choice does not allow simplifying the convection equation either to a form similar to the equation of Busse approximation. I just remind you that Busse approximation perhaps is the easiest form, or even to a form allowing efficient numerical modeling. And it is more natural following Braginsky. There are many authors. Braginsky perhaps was the first. Braginsky. Then it was Roberts, very famous person. Then Whitun mentioned myself. So also I put some effort to prove that it's not convenient to use thermodynamical variable like P and T, but much better to use entropy and density. So as the main thermodynamical variable, since the deviation of the adiabatic state is extremely small, so why not? It's much better to use the entropy as the main thermodynamical variable, just because the the deviation of the all this entropy from the entropy value which is correspond to adiabatic state is very small. It's actually tiny 10 to minus 4%. So it's very accurate from one point of view and very convenient from another point of view that it gives much more simpler equation than if we use pressure and temperature as the main thermodynamic variable. Much more better to use entropy and corresponding modified pressure. So so accordingly, the equation of the nearly adiabatic state of the matter closing the convective system 4.1 can be written in the original form. Let's write it down in the original form. Maybe here we. Okay. Here, yeah. Okay. So let's write down the equation of state. And this equation is related, let's put I, Jonas. It was even articles with me and Jones who discussed this stuff. So eventually we have equation which states the state equation, and it could be written like in terms of the density. So density, which depends on, in this case, as we already agreed all together, that we use as the main thermodynamic variables, we will use thermodynamic pressure and thermodynamic entropy, just two of them. And rho will be expressed somehow, and this is the equation of state. And of course, we write it down in the differential form via the adiabatic density, from which we just slightly derivate. And also there is two terms. One term in this notation has the sign plus, and so there is the p component of the density, quite well determined. And here we should put the minus because the entropy working is in somewhat another direction. Here we have component of the density, S component or entropy component of the, oh, sorry. Here I omit. I omitted here P. So from capital P, we jump to the small p, which is just deviation. Small p is just deviation from the some capital Phi. And here there is index for the density P, which denotes that it's contribution from the variable pressure. And also there is variation in the entropy. So we have rho with index S, which also very well defined. And here we have small s, which is just variation from the adiabatic states. And this is constitute the formula 4.1e. And all the coefficients which appear here, this coefficient, this coefficient, this coefficient, are rather well defined. Let's write it down. Let's write them down. Okay, then I remove the rest. So even by definition, we can write these things down. First of all, of course, the adiabatic density, this one, is rather well determined directly from the seismical experiment. So if we consider the case of the Earth, so this adiabatic density is rather well determined from the scratches. So let's just stress this, that this thing is rather well determined. This also relatively well determined, and it can be represented like that. So this rho p is actually identically equal d rho by dp with constant s, b rho by dp. In the condition of constant s, usually it's written like that. And in fact, it's the inverse sound of speed value. So if we consider the sound of sound of how it's in English again. Speed of sound. Yeah, speed of sound. Yeah. Excuse me, I forget. So it's just the inverse square of the speed of sound, and this value, which is coming from here, this one. And another value from the direct thermodynamical variable is going like that. The adiabatic component of the density. And it's by definition, again, quite similar stuff. We are getting derivatives with respect to the entropy now. So we getting derivatives with the entropy on the condition of the constant pressure. So we put it like that. Here's the capital pressure. Let me stress that. So, and it has some simple representation with the expansion coefficient, adiabatic temperature, then adiabatic density, which is quite well known, and also it contains Cp value. This is just thermodynamical relation, which is quite general one, so I will not number this formula. So let's proceed further. Let's just know that for the Earth, this you know that actually this speed of sound is variable, but let's consider at some particular places. For example, for the Earth at the outer core, so like we have agreement with you, the outer core, we notate like C with index O. So at the outer core, this speed of sound is a rather big value, by the way. Okay. And it's quite precisely could be measured. And if we consider Ci position, then this speed of sound is even greater because the density becomes greater. It's about 10 to, and it's a rather well determined value, meter per second. And then according to the seismic data, actually, with accordance to the seismic data, we obtained that. And there is a list of the authors. I will not write them down. I just sound them. It was Dembowski and Anderson, Kenneth et al. And they determined that this expansion coefficient, perhaps this expansion coefficient is the most important thing because it's come directly to show us how this expansion is happens, and it's exactly related to the position as we discussed with you. If we make some additional heat, or maybe remove some entropy, in other words, it's actually equivalent. So there is some heating of the part of the liquid, and it's going up. So, and namely expansion coefficient responsible for that. It's actually show how much per every degree we can expand. So it's actually in the US core, it's also could be measured in accordance with the seismic data. Again, near the boundary, near the outer boundary, its value is about 10 to minus fifth per Kelvin. You see that it's relatively rather small variable, but you should take into account that you multiply this by the temperature, which 1000 degrees in the core. And also, finally, if you will estimate some things, you should multiply on corresponding density. So the density contrast will be rather sufficient to derive the convection. And so, okay, and alpha E is a bit smaller. Alpha E is a bit smaller, and it's about 10 to minus 5, the same 10 to minus 5, like there, but without 2, again, over the Kelvin. Of course, this here you see that maybe for this estimation of this expansion coefficient, accuracy is much less than when we estimate the speed of sound. So, of course, there are another authors who quoted slightly another values. And also, very important thing is thermal conductivity coefficient. And so there is also different coefficient which is appear for the different approximation. Perhaps there are plenty of them. I don't know. Maybe it's not worth to write them all down because actually you can find them somewhere in the record. Just for example, I put some values from here just to show you that it's quite well understood and quite easily could be estimated. And there are a number of authors who estimated different value for the Earth. And also, of course, there is the model of the planetary interior in this corresponding region where the convection happens. But eventually, I think that this text will be available to you. And nowadays, by the way, there is some correction sufficient to all these values. So maybe it's better to use nowadays value. So let's proceed from this estimation further. So the convective variable used below and included the equation of state for 1e, this equation of state, this sort of the convective in the comma, so this is convective, that is just deviation from that is the deviation from the variable. So it will be written like that. So just by definition, we define the small deviation of the pressure, and it's of course is equal real pressure minus adiabatic pressure. Then we of course define in the same fashion via the convective variable. Via the convective variable gravitational potential. So small u, just by definition again, is equal u minus u adiabatic. And of course, for the entropy, we play the same game. I write it here. We have small s, which is difference between real S capital and adiabatic S. So, of course, there are another variable. There is also temperature. But here, when we consider the temperature, so, or otherwise like that, temperature. So, in fact, we consider the temperature minus adiabatic temperature. And because we already make the agreement not to use the temperature as adiabatic variable, but use the entropy, so this difference we should express in terms of the entropy and pressure. And in this case, it will be T with index P. Again, this similar things to that. Is thermodynamical variable and thermodynamical. So here we take the play the same game. We make the derivative, partial derivatives from the t over the s and under constant pressure. And here we multiply by small p. And the similar way we have a plus t, which is actually very differential, and it's working under the constant entropy. And here there is S. And we can even express all this stuff more precisely if we consider adiabatic temperature divided by Cp divided by Cp, then we can take into influence the expansion coefficient. Let me write it in maybe more convenient way, like alpha divided by adiabatic density and multiplied it by small p. And finally, we have addition of the small s, which is going out from the entropy in this way. So finally, we have 1, okay, I'll put here a comma, 1, 2, 3, 4 deviations, and it's all this constitute formula 4.2, and it start from A and end up D, A over D, all this formula. So exactly 4 relations. And all these 4 relations means that there is a very tiny deviation from the adiabatic state. And so eventually we can put it in the original equation and then to see how it's works. So maybe at the moment we will stop and have a break. Yeah. Is it working, yeah? Okay. Excellent. Okay. O1E. Then we determine all these things. Then we have 2, 4 AD. Then we describe equation in the sort of the convective variable. So this convective variable, which we finish it to write down somewhere here, but I remove this, that it will not grab your attention. So, as far as I already told to you, we have so-called convective variables, convective, of course, in brackets and commas. And these convective variables are very small, even to say tiny difference from the adiabatic variables, corresponding to adiabatic variables. So all this which is written here, all this value are renormalized, and now we have in small letters just deviation from the adiabatic condition. In some sense, even velocity, which of course we put in capital letter, is also some deviation from the adiabatic state, because adiabatic state is correspond to the zero velocity. Okay. Let's proceed further. Okay, so we define these convective variables, writing down them all in relation of other parameters, and especially from the okay, describe derivation from, so all this so-called convection variable describe deviation from the adiabatic state that are less than 10 to minus 50%. So just let's state this, the deviation from the adiabatic is just 10 to minus 5%, so very small. So the accuracy of this approximation is really very good. So it's just it's less than 10 to minus 50 to minus 5% of the original variables in the liquid core of the Earth. And there I work Braginsky, Roberts, and myself, and also by Jones, which proves that. And in the adiabatic state for entropy, depending only on time, so actually by definition in adiabatic state is this adiabatic entropy. So if we take the gradient of the adiabatic temperature entropy, it depends actually only on time. So any gradient of adiabatic temperature is obviously zero. So, and this is working in the perfect direction. So we have only time dependence. Let's just stress it for adiabatic state. And this is very important point. While it's not numbering again, because it's some sort of the general stuff in the adiabatic approximation. So it's exactly depends only on time. So density, pressure, temperature, and gravitational acceleration. So there is a still remains some density, adiabatic density. There is adiabatic pressure. There is adiabatic temperature, of course, and gravitational acceleration, which is actually constitute gradient of potential, also adiabatic. All these values depends in general on both time and spherical radius r. It's important to mention that the dependence for all these adiabatic variables, which are here, I'm just listed here, is only, let's state it on, of course it depends on time as well, like the adiabatic state, but also it depends on spherical radius. So actually we are looking for the equilibrium state and taking into account the radial dependency. And here, all the adiabatic values, which I just listed here for you, are very well known in the Earth core, in the Earth liquid core. They are very well known because it's possible to estimate them just from the seismic observation. So you're just using the seismic wave, and even from atomic weapon, which was ages ago, and so from this the sounding by the waves, by the sound wave, we can very easily estimate all these parameters and almost with very big accuracy. Of course, less than this deviation, but still rather big. So let's state again that all these variables in general depend on both time and spherical radius r. Since only the change in entropy over the time significantly affect convection, considered here at times much shorter than the global evolution time. It's also important to note that we to have our restriction on time and to simplify in this case, of course, we are working in the time which is much less than all the history of the Earth. We are not operating by billions years, and even we are not operating by millions years. We just happy to operate with some 1,000 years. So it will constitute very high accuracy of this all adiabatic approximation of the interior. We further assume that all thermodynamic quantities, with the exception of entropy, depend only on the radius r. So actually, it's very good approximation, and the derivative of adiabatic temperature, the derivative of the adiabatic entropy with respect to time, that affects convection. That's only affect convection. So actually, we have this. We can write down that the direct derivatives of SA, because it depends only on time. Yes, so this direct derivatives of S could be on time only. So, and this actually drives the convection in some sense. More precisely to say that it's minus, with taking into account the minus. So it's based actually on definition again given by of the entropy in Landau and Lifshitz. And we can even roughly estimate this value as the ratio of the heat from the flow from the liquid layer divided by its mass and some average temperature. So we just can, we can rewrite these things in more simple and maybe more easy to operate way, just using the dot on the top. So, and we can estimate this capital S via the, first of all, of course, it's equal to this, and then we can proceed that it's equal to some heat flow, which is represented in the terms of the outward flow. This is just a heat flow, which is measured in terawatt, for example, or just watt. And so this could be estimated from this very general point of view. Okay, let's put here that this is approximative estimation. Like QO divided by the mass of the core, which is also quite well known, and divided by the average temperature of the core. I put here the core, the C indexes, because it's related to the whole core. To the whole core. Here. So this constitutes the formula 4.3a. And this is just the rough estimation, but of course it can help us to understand the physical nature of this stuff. And to define S dot more precisely, the original energy equation 1D and the boundary condition 6 on the radial derivative of the entropy should be used. For example, we make such an exercise in section 4 below. And the mass average superabiotic entropy is always zeroed out, actually. So this mass average, if we make this mass average of all this stuff, then it's, by the way, why there is no minus here, because usually for the current situation in the Earth core, this adiabatic gradient is negative. So actually we estimate this adiabatic gradient by the inverse t in this value. So here we can take the plus. So let's proceed further. And so finally, we also should satisfy to the integral condition. Maybe at this moment it's clear that we, if consider the integral contribution of this all entropy, so we need the satisfying the integral condition, which is related to the entropy integrated with rho, because actually this is sort of the conservation law. So in all volume, and they are integrated over the all volume from R greater or equal Ri and lower or equal Ro. And this integral should be 0. That means that actually, when we consider the convection, later we will see that we are imposing on for the entropy boundary condition not on entropy itself, but on its derivatives. So if we impose this boundary condition later, I will of course to say it more precisely, namely because at the moment it's better to define this stuff. So actually we should cancel out all the deviation from the entropy. And actually this integral is working exactly in this way to cancel out, just to keep near the adiabatic state. So taking, okay, let's remember this formula. 4.3 B. 4.3b. Taking into account the smallness of deviation from the adiabatic state and the obvious, for example, it's written in work Braginsky and Robert 1995. So we can make sort of the obvious estimation. Let's write them down here. If I fit, I'll try to fit. Braginsky and Roberts, they estimated gradient of the gravity. Then it could be estimated via the Laplacian, via the pressure, like that. And also we can estimate Laplacian of the gravitational potential. I just remind you that it's just Newton law. So using this thermodynamic relation and using just Newton law, which we already write down. All this stuff actually could give us very simple relation that adiabatic density is obviously the function of the thermodynamic pressure. So all these things are resulting from the adiabatic hydrostatic, and we transform the terms in the very first equation, which we showed to you before. This very first equation, this equation which relate the entropy, and this relation which is actually Navier-Stokes equation on the bottom. No, it's repetition. Okay, you see that with this we make these two things, and it leads to the it's related like that. So, and then we can use Archimedean. We can identify the Archimedean acceleration. Actually, all this game is just to identify the Archimedean acceleration that contains the pressure term. So eventually we have a bit lengthy formulation. Maybe I will not repeat it. So there is a bit lengthy formulation which is written here. Perhaps I will not repeat it on the board. You can see it here. So you can copy if you like. I just comment on the different term. So resulting from adiabatic hydrostatic, we transform the terms of equation, of initial equation, containing the pressure and Archimedean acceleration. So actually we use a momentum equation. And then we balance gradient P over rho via the gravitational potential. Then it works like we use the thermodynamic relation. So we relate this gradient P over R. Then we relate the remaining term. And finally, we see that there is, for all the stuff, there is sort of the Archimedean source, Archimedean buoyancy source, which is represented via the deviation of the entropy. And also there is some reduced pressure. You see that here we involve gravitational potential under the nabla term, and also we involve the this pressure, deviation of the pressure also over for RR. Perhaps you write it down, I will give you possibility. So I will not repeat it on the DOS, on the table. Hopefully you could write it down. And that is the final equations for the velocity v and the gravitational potential u take the form. So finally we can write down, now I should write down the resulting equation, which one, this one on the top. Let's write down because it's actually very important equation. So I will write down and connect it and comment it. Okay, maybe I'll remove from the top. It seems that on the top we have things that we don't need anymore. So let's remove them. Okay. Let's remove them all, just to have a free space, because actually we are about the very major conclusion of all this stuff, about the final form of the equation, which is already dissolved its own blank list. Okay. So we are writing down momentum equation, equation for the gravitational potential, and then all other equations we need to solve this problem. So of course momentum equation is just slightly changed. we have dv by dt, substantial derivatives. Then again we have viscosity term. Okay, let me, for the case of the Earth, keep only first term, because the second is not so important. Let's omit it. Then there is the Coriolis force as well, one of the most important. Then there is one, maybe the most important term which we eventually get during all these exercises, but it's not so big, but very valuable. So this is the term which related to the entropy. So it starts from the S, of course, because the S is the most important, small s, I stress that the small s. Then there is expansion coefficient with temperature, corresponding temperature, adiabatic temperature. Then it divided by, then it divided by Cp, and also there is gradient of adiabatic gravity potential. So this is the main term in all this kitchen. Let me stress it. And actually it's direct analog in Bussenesque approximation, the term which is connect T with alpha, but in their case this T not adiabatic T, but just the deviation T from the some equilibrium state. But here it's more correct equation and much more exact than Bussenesque one. And of course there is a pressure here, but not simply pressure, but modified pressure under the nabla. It includes gravitational potential deviation from the adiabatic state, and also it includes the modified pressure, which could be written in the simple form. We have again deviation from the adiabatic state and just on the density, adiabatic density again. So it's equation 4,4a. And then we proceed further. Of course, we should keep the equation for the gravity field. And this equation for the gravity field is, in this case, a bit simplified, because we have representation via the pressure and entropy, but not have representation via the density directly. We involve it indirectly. So we just consider the deviation of the density corresponding and express them in terms of the pressure and entropy, not the density itself. So the gravity potential should be written in slightly another way. Here there is a gravity potential, and here there is, since we already see, so we have, we have the derivatives of rho component under constant pressure, and it's of course multiplied by deviation of the pressure from the adiabatic state, and then in a similar way but with minus sign, it's just because the thermodynamic variable are fitted in this way, we have derivatives of the adiabatic gradient, adiabatic density under the condition that the entropy is constant, and here we multiply by small. Okay, then we have, of course, we should have the continuity equation. The continuity equation could be written in this case like that. So we just, let's make some transformation to the continuity equation. We can use again these brackets. So we just make derivatives of again rho p exactly the same, minus rho s. And after differentiation with respect to time in the substantial derivatives, we obtain the simple relation minus v over grad or a minus rho a divergence of v. All the stuff could be even further simplified, so it will be just divergence of rho adiabatic by v. All of this is 0. So this is the direct consequences of the continuity law. So we have for phi a, this is for b, and this is for c. And then, of course, we should write down the energy equation, or you can call it entropy equation. It's actually, in this case, the same. So we have entropy equation CA, TA, rho A, continuity equation T, and it's equal. Of course, we repeat the same equation. We have gradient of the transfer coefficient multiply again this bracket. Again, we use this bracket, but not exactly this bracket, but in relation to the temperature, of course. So in this case, we have Tp plus, sorry, not Tp. Yes, Tp multiplied by small p. Again, the derivatives of the temperature under constant pressure. Then plus the same, but at the constant entropy. And here there is small s. And perhaps maybe you remember that after that it was QA, but of course in our case this QA is exactly specified. So just instead of the writing QA and separately defined it, okay, let's nevertheless put it, not be too much in a hurry. Let's keep Q. We better write down it separately because it dissolves. So, because actually the major source of the heat that produces convection. So this is 4d. Okay. And now the superadiabatic power of volumetric heat source is defined in 4d as, we will not write it down, it dissolves the special numbering for this superadiabatic power of volumetric heat source. So let's write it down, that Q small q, small in value but rather big in the importance. So it's exactly could be related like even by definition. Let's suppose that it's given by definition. So first we have deviation of the temperature. K gradient TA. So we have divergence from gradient from some combination of transport coefficient on gradient of adiabatic state. Let's name it adiabatic state, adiabatic contribution. And then there is could be, oh sorry, I forget put here co-adiabatic, sorry. I missed that. In this formula 4, yeah, I forget to put this index, please put it. So, and here we express adiabatic, this adiabatic term in this value, like that. Then there is some additional term, for example, magnetic or whatever you like, term of this heat source. But of course, in the first approximation to model convection, which has just neglected. But for the case of this, because this source could be radioactive or other sources. So actually we have here plus Q, and also we have the contribution from the entropy term, entropy which is going on the top of everything, and here we have the precise value rho A T A and direct derivative to the entropy. Of course, the initial entropy, not deviation from the entropy. It's exactly from which we deviate. And it depends only on time, as we already talked with you. Okay, so it's a separate formula, quite important. Okay, let's proceed further. And the first term here is negative. This first term is negative, actually. The first term here is negative due to the divergence of the adiabatic temperature gradient. You know that if we go in from the bottom, from the very deep interior of the liquid core, for example, if we stay near the rigid core, it will be the highest temperature available. So if we go up, the temperature becomes to diminish. For example, at the inner core boundary, rigid core boundary, the temperature is about 6,000, like on the surface of the sun. Then if we go up, then temperature diminishes, and it's reach value about 3,000 near the boundary between mantle and the outer core, the outer liquid core. And if we go in further up, then we see that there is a mantle, and it's diminished up to the comfort temperature about 30 degrees here. And so you clearly see that with rising of the radius, we have declining of the temperature. So it's exactly constitutes that this term has negative number, negative value. So it's negative because the gradient is negative, adiabatic gradient negative. So the first term here is negative due to the divergence of the adiabatic temperature gradient. And here there is a rule which was invented by Grinson. I don't know, pronounce him correctly, Grunizen or Grinzen, I don't know, but something like that. Let me write down. This is definitely German man because on Norwegian because he has these two dots on his family. He is responsible for the following law, which is perfectly working in the adiabatic state, that the adiabatic temperature, for example, on some boundary, is related to the temperature of the inner boundary, which of course is the boundary with the rigid core. And here we just have relation of the densities with gamma, small gamma. This gamma is namely named the Grünizen, if I can pronounce it correctly, Grünizen. Let it be Grünizen coefficient. And he invented this law. And of course here we have again, of course, near the inner core with the same Grünizen coefficient. And so this thing is working as equation 4, 5b. So here gamma is Grünizen parameter and Ti is the crystallization temperature of the inner core. It's important to mention here that exactly you know that when we have the impurity, which is more heavy impurity, which come to the rigid on the boundary with rigid core, so it becomes part of the rigid core. And it's obvious that if we come from the liquid state to the rigid state or crystal state, so it will be responsible for some crystallization temperature and some additional heat. So the positive second and third terms for 5, 8, the positive second, this one, and third, this one also positive because dSA by dt is negative, so it's also in total it's positive. So the positive second and third term in 4.5a describe local heat sources in the core, and for more details you can examine some appendix, and the heat flux due to the global cooling of the entire core. So actually this is because of the cooling, this term, and this, and it's estimated, okay, we remove that, but nevertheless, this is the cooling term, and this can include everything. It can include radioactive, and can include magnetic. By the way, magnetic is very important if we take into consideration magnetic field. And it's the only contribution here, so it's quite general expression. So favorable condition for convection development will be where core is positive and vice versa. So if this is okay for this is necessary that derivatives of the entropy is less than 0, and so it's take positive value and develop convection. And this itself contribution, if it's positive, but it also could be negative. It could work like a sink. So in this case, it supposes the conversion. But more ordinary case, when it supposes the conversion. So the convective system 4.4 is closed by the condition 4.3b. We showed it previously. Can we? Okay. Here like that. 4.3b and 10 boundary conditions. So there is a this 4.3b condition, this integral condition, and there are 10 boundary conditions. Of them, 6 are obviously from the velocity. For example, for rigid boundaries, they could be written like that. So first 6 boundary condition for velocity. Let's state this boundary condition for velocity is they could be state. First of all, let's write it in some new form. So velocity at r equal rho at the outer boundary is actually identically equal further like VO with index O, and it's of course equal 0 because we rotate together with the mantle. So, and then the next boundary condition is at the inner core. Okay, sorry. And then in the similar fashion we write down them. Okay, R equal Ri inner core. And in our case, we can use the simple formula which we actually made on the very beginning of our first, second, and maybe third chapter where we started with the differential rotation. And this differential rotation can be stated in this notation like that. Sin theta. Angular rotational rate, which is the imposed differential rotation. Normally it's taken like a constant. And here we have unit vector in direction of phi, which constitutes the differential rotation. So this is boundary condition for velocity, 6th boundary condition for velocity for point 6, A and B. A and B means that A is on the outer and B is on the inner. So here, as I already mentioned, omega I. Sorry? No square. It's just this R sign is corresponding to the cylindrical radius there. Yes. Oh, no. Here you can mistake this S with this S with. Here you can mistake this S with. Just state correctly that it is cylindrical. Cylindrical radius. So there is no square, this is just R sine theta is the cylindrical radius. So actually this cylindrical radius go in front of the angular rotational rate, and so then it creates the final velocity. We just multiply the angular rotational rate by corresponding radius. And so we have the velocity. In terms of velocity, we have that. So here omega I, as I already told, is the angular velocity of the rotation of the inner solid core, which is determined by the viscous moment of forces. In the following two boundary conditions for the parabatic entropy S, which again the number of us, Braginsky, Robert, myself, and Jones, Glatzmeyer, and Roberts. So we use the temperature Ti and To's correspondingly, which are on the inner and outer core, and densities for I and Rho, and the heat fluxes Qi and Qo specified on the boundary. Of course, we have at the moment we have 6 boundary conditions and 10 equations. So then we have we could have 2 energy boundary conditions which impose it on the entropy and state how many energy is going out and how many energy going in this liquid shell. For example, from the rigid boundary, we can go to the liquid shell, and from the mantle, we can also somehow cool this inner shell. But anyhow, let's write down this boundary condition for the entropy. It's new stuff because actually we didn't write them at all. So let's write down now and comment correspondingly. Of them just estimated. So let's start from the inner boundary, of course. On the inner boundary, we have temperature exactly at this boundary, adiabatic temperature, of course. Then there is density, also straight there. Then there is a kinematic transfer coefficient. And then there is the derivatives of the entropy. As I already told to you, that we have partial, we have boundary condition which is stating not the value itself. We don't equate the entropy to the, but we equate the divergence of the entropy. More precisely, it's just gradient in radial direction, and this gradient is directly related to the heat flux. So we should play this trick that we define the boundary condition for the entropy via the derivatives, and one, of course, boundary via the derivatives, and another boundary via the derivatives. So in fact, to fully satisfy to this system, we need another integral condition, because we have the boundary condition for the derivatives. So we should have another additional boundary, not boundary, a global condition on all the space. And it's working like this integral condition. We're taking into account adiabatic state that divergence of S rho is equals 0. And so actually we take this integral form, and then we just remove all the in sum of all the divergence from adiabatic state, and it's just cancel it down on the total integration. Let me finish with the boundary condition on the entropy. So this is the inner boundary condition, which of course have, if we denote by Qi total heat flux, which is coming out from the inner core. It's coming out because we somehow cooling down the inner core. So this is total heat flux. In this form could be divided on all sphere, could be divided on the area of all sphere. Obviously, this area is 4p Ri squared. You see that this relation don't straight involve the heat flux and corresponding entropy flux, but it's in some sort of related units. So we consider the, for example, watt per square meter. So we consider the flow, not flow itself, but in relation on the area. So we relate it on the area, and of course the area of the boundary of the inner core is 4p Ri square. So, and then there is another term which constitutes the adiabatic gradient. It now works with capital transfer coefficient, and it just includes direct variable of adiabatic temperature over there. So that it's all on the inner condition, inner boundary. And the similar stuff, of course, could be written for the outer boundary. Here we have, again, minus T, but now O, rho O, it's quite symmetrical stuff. Small k over, again, radial derivatives of S over dr. Okay, I didn't finish here. Of course, we are taking these derivatives near the boundary. So we take it here. And these derivatives as well we are taking near the. Okay. Yes. And these derivatives, of course, we are taking at R equal RO. This is at the outer boundary, the same play. We have QO divided by the area of the outer boundary now. And then we have contribution from the correspondent adiabatic temperature gradient. Because as we already told that we neglect the time dependence in all these adiabatic variables because we are working on not so big scale to keep that stuff. So we just neglect them. Temporal in time dependence of time for some adiabatic state. The only one which we not neglect is the adiabatic state itself because it depends only in terms of the entropy, it depends only on time. So, and it's correspond to the cooling down the system. This in the previous equation, which I showed to you, it's of course included. Here, well, like this. Okay. Like this. Here. Okay. So, nevertheless, so here there is some relation between these two transfer coefficients. So the kinematic transfer coefficient which we denote by the small k is usually greater or equal like the dynamic transfer coefficient. Actually, it's another coefficient. One is related to the entropy, that is related to the temperature. And to make it at the same units, we just divided it by rho A CV. And so, and always this, usually that stuff has turbulent nature. And here there is such a relation between these two transport coefficients. And it's usually turbulent and transfer coefficient, or equally possible that it's only for molecular quantities. And in the right hand side of 4C, well, I didn't number it, sorry. Okay, let's say put number here. I forget to put the number. 4.6. C is the first one, of course. And then we, I forget to put, no, I put comma. And after that, there is D. Okay, let's number this formula consequently. So, in the right hand side of 4C, CD are the difference due to typically negative gradient of the adiabatic temperature between the given and adiabatic heat fluxes. You know that this is the given flux, which we can do from the boundary condition. And this is the adiabatic heat flux. And because I just discussed with you that this adiabatic heat flux contribution is negative because it's diminished with it. So actually it's become negative, and so there is some sort of the deviation. More precisely to say that here on the boundary condition we have deviation. So if, for example, we consider in terms of the temperature, then we have that if we exceed with this QO, we exceed that one, then we have superadiabatic condition, and convection could be developed. In the but by the way, opposite case is possible. So it's quite possible that this output flux is or input flux, whatever it is less than adiabatic heat flux. This one. So in this case, we have sort of the situation when we are opposed to the convection. So it will be subadiabatic case. We should have subadiabatic case, that the adiabatic value is non-adiabatic, given value of this flow is greater than adiabatic one. Again, I stress that effectively here we have minus. And so, and actually this allows us to understand how these things work. And it's quite tricky situation that we have two boundary conditions, on the inner boundary, on the outer boundary. So it's possible also situation that, for example, on the inner boundary, we have the condition that satisfies to development of convection. But on the outer boundary, condition could be not satisfied. So it could be not enough heat fluxes which is coming out from the outer boundary. And if it's less than adiabatic heat flux, then we have sort of the stable layer on the top of the convection zone or near the outer boundary. In this case, if we are not exceeding adiabatic heat flux, we have sort of the stable boundary layer, and in some observation and some experimental estimation, this is indeed true, that we have boundary from the outer inner core, but from the outer core it could be prohibited. So, okay, the remaining boundary condition requires that the entire gravitational acceleration coincide with the gradient of the adiabatic potential at the boundary. So actually this condition on the adiabatic on the gravity potential is quite simple. It's just du by dr is equal actually not. It's very simple condition. But here we could state that it's even satisfied on both boundaries. So we can state it at R equal or O, and we should state it. And at R equal Ri as well. This is rather simple condition with the gravitational potential. And so it's we numbered it 4.6 E and F. So in was a further to simplify the system for 3b, for 4, and for 6. For 6 it's here, for 3b, for 3 is here. Okay, for 4 is here. Okay. In order to simplify the system significantly, we first estimate the pressure Laplacian form from 4D. 4D. Okay, it's not here. I lost it. Yes, for D is pressure Laplacian form. This one. Okay. We first estimate the pressure Laplacian form from 4D. To do this, we take the divergence from 4,4A, from this one, and substitute the gravitational Laplacian from 4,4B and compare the corresponding terms. We conclude that gradient squared of P by the model is of the order of Coriolis force with this addition. Here R omega times grad V. So after manipulation with this equation, which was shown here, we can get the same relation. So it's due to the dominance of the Coriolis force. The part of the Coriolis force is included here, but here we have some derivatives of the fit. And then, due to the dominance of the Coriolis force, accordingly, the term proportional to Laplacian P, this Laplacian P could be obtained from the Navier-Stokes equation when we take the rotor of it, or more precisely, the Laplacian P could be if we take the divergence of this equation. So if we take the divergence, we give rid from this, but keep here the divergence, the Laplacian, and also we have some contribution from this and this term. So accordingly, the term proportional to nabla squared of P on the right hand side of 4B, of the right hand side of 4B. Okay, I lose some stuff. 4D. Okay. I don't know, maybe we already passed 1 hour. I don't know. Because I'm a little bit become confused and forget something. It seems that we already spoke 1 hour. Perhaps we will finish at the moment. I think that we spent more than 1 hour. But nevertheless, maybe there is some question. Okay, please. 4.6E.
No, that's the left one, first one. Okay, greater than.
The first one.
This one? Yeah. Yes. Comment on it? Yes. The comment is that we have this transfer coefficient. This is dynamical transfer coefficient for the entropy. And usually we estimate this.
For the entropy, we use some consideration of the turbulent nature. And in this case, this coefficient of the turbulent nature, while this coefficient it's initially dynamical coefficient with capital K, but if we divide it by this value, so it will be also kinematic, just to compare with that one. And so, and it's somehow fixed from the molecular value. But this is not so well determined. And if we use molecular value for this coefficient, then it's just equal. If with this molecular value, then we have this equal. And only in this case. But usually people use, and to reach the molecular value is somewhat quite difficult, because it's too small. And so usually people choose much larger transfer coefficient, this one. This usually is known well, but this will known not so well, and very poorly. And people argue that this is turbulent coefficient. And this turbulent coefficient is much larger than corresponding kinematic molecular coefficient. And so they work and they solve the problem. Okay. Is there any more question? 4.3. Okay. Let me see. Where is it? Okay, I see this.
So equation 4.3, what does MC represent?
MC is the mass of the liquid outer core.
And TC is the temperature of that same liquid.
MC, M with index C. You mean, yeah? This
Mass
TC, yes,
of liquid
yes,
core.
of course, the average temperature of the liquid core. TC is the average temperature of the fluid outer core. And MC is the mass of the fluid outer core.
And so the lambda coefficient.
Which coefficient?
So, lambda coefficient you spoke about.
Lambda coefficient. Where it appears near the which formula?
Sir. 4.1b momentum equation.
4.1
B.
G.
B. Momentum equation.
Yeah, momentum equation, yeah.
So the lambda equation coefficient specifically represents. So what does it represent specifically?
Lambda coefficient. One which is near the divergence or gradient of the divergence.
With yes, with gradient of divergence.
Yes, this lambda coefficient is just sort of the constant which is following from the material property of the
Material
flow.
property.
Material
property.
Yeah, but mainly from the, you know that in the case when the density sufficiently, when the, actually it depends on the divergence of the flow. If divergence is rather large, then this coefficient is important. But in case of the Earth, this coefficient is not so important because the divergence of the velocity is not so much.
Okay, sir. Thank you.
Okay, thank you. Yeah. The reason is that the just divergence is very small.
Okay.
Because the divergence in the condition of the Earth, of course, they are very small, and the planet as well.
Okay.
And this divergence come out from the variation of density. And for example, in the Earth case, there is just 10% variation of the density from one boundary to another boundary. But in the Sun, if we apply the same scheme to the Sun, then we have 10 to 7, 10 million times. Density change 10 million times, not just 10%, but 10 million times. So, of course, this term becomes very important here. But in the case of the terrestrial
Planetary
planet,
convection, we are neglecting.
yeah, we can neglect it. Okay. So, we will finish. So, we spent more than an hour, sorry. Much more than 1 hour. Okay, maybe we will finish for the moment if there is no more questions. Let's finish. Thank you.